So we have discussed different methods of generating the SSB signal, the single sideband signal. So in this video, we will now discuss how to perform detection of single sideband modulated signals. Now, single sideband, if the signal, single sideband signal we have, if it has the carrier, so it's called SSB plus C signal, and we can express it in this through this expression. So where this part is a single sideband signal without the carrier, and when we add the carrier to this, so it becomes SSB plus C signal. This can be recovered by synchronous detection. First of all, when we multiply this signal by another carrier, a local oscillator, and if we can remove the carrier component, this one, so by using narrow band filtering, then we can get our signal back, the signal empty. Alternatively, if the carrier amplitude A is large enough, so if this amplitude is large enough, MT can also be approximately recovered from the envelope or rectifier detection techniques that we have discussed in other videos. So let's look at some mathematical expressions related to this detection of SSB signals. Now, the SSB plus carrier signal, the mathematical expression can also be written in this way, where we have taken out A plus MT, and so the terms with the cosine signal have been written on one side, and the terms that are with the sinusoidal signal are written in a separate way. So this is the, as you know, this is the Hilbert transform of the message signal MHT. Now that means by using a trigonometric identity, we can write this signal, rearrange this signal into this expression, where this ET is it can be extracted from the real and imaginary part of this expression by using this mathematical relation. And if we open this mathematical expression further and take out A outside, so we will see that we are left with the expression here. So we have A, we will have these three terms when we open this A plus MT whole square, and the term with the Hilbert transform appears over here. So since we have taken A as common outside, so we have A in the denominators and A squares here in the denominators, right? So the square root appears as it is. Now this is the expression for ET. We can see there is a theta also that appears here. So as you can imagine, this can be obtained by tangent inverse of the imaginary part, or the part that is at the right angle to the this real axis. So that is on the in the numerator, and then in the denominator we have this part that is written with the real axis, the cosine term. So now from this expression, if we can see that there are certain changes that we can make if the amplitude of the carrier is very high, compared it's much higher than the magnitude of the message signal, then that means that this A would also be high, much higher than the the amplitude, the magnitude of the Hilbert transform of the message signal. So these two terms, they generally are valid. So that means the terms that have squares in them, and we have in the denominator we have A square, so these terms are very small, and hence we can ignore them. So the previous expression for ET is now reduced to this expression, right? So by using Taylor series expansion, and by discarding the higher order terms, the terms that have MT by A in them, they can be discarded because these terms are generally very small compared to 1, that provided if A is much greater than MT. So when we do that, we are left with this expression. So by using Taylor series expansion and ignoring these terms, we are left with this expression, right? So that means this ET, the signal, received signal, is proportional to, or it's almost equal to A plus A into 1 plus MT by A. Now if we multiply this A inside, we are left with this expression. So you can see this received signal ET is equal to, approximately equal to, this A plus MT. So this is, where did we get this ET from? We got this by multiplying the received SSB signal with a local oscillator cos omega ct, and after rearranging we saw that the result is almost equal to A plus MT. So that means, but this is only true if we have a large carrier component, that is the amplitude of A is much larger. So then the SSB plus C signal can be demodulated by a simple envelope detector, right? So this signal can now be simply detected by an envelope detector. So in AM, the envelope detection requires this condition. So in the general AM, the full AM, where we have both the sidebands, if you remember, the conditions for envelope detection were that A should be higher than or equal to the magnitude of MT. But for SSB signal plus with carrier, the condition is that A should be much higher than the magnitude of MT. So in SSB case, the required amplitude of the carrier is much larger compared to full AM, and so that's why generally the efficiency of SSB is very low, because most of the power is transmitted into the carrier, which is then discarded anyway at the end, so the efficiency is quite low. So this was about the detection of SSB signals. If you have any questions, you can ask in the comment section, and please don't forget to subscribe to the channel. Thank you.